Morning, everybody. I'm very glad to be here today to share, I guess, my special interests for databases and the technology that makes them work. Probably we've all spent a fair bit of time using databases and not thinking about it too much in terms of how they were built or what goes on inside them to help them do the things that they do. But I want to convince you that they're actually very interesting and amazingly sophisticated bits of software. I won't be talking about how to use any particular database tools or how to choose the type of database to use in any particular situation, any of that kind of stuff. My focus is really on database internals and what it would take if you wanted to build your own database. Thank you to all the sponsors who make this happen, I suppose. I particularly want to call out the coffee cart sponsors because I get plenty of value out of them. Seek is the company that I work for, so while we're talking about sponsors, they've paid me to be here. So, and if you do your sponsor bingo, these are some of the fun things that can be yours. All right. Before we get right into it, I just wanted to warn you and say that it is going to get pretty nerdy. I know that there's a fashion for these things to be kind of light and entertaining, and that's great. I like those as well. But I also think that it's nice sometimes to have some kind of deeply technical content to challenge ourselves with a little bit. So that's what I have gone for here. And I wanted to start out really by offending everybody and making a criticism of commercial software development. And my criticism is essentially that our industry forgets everything it knows on a regular cycle and then reinvents the same idea. A new thought leader comes along, they put a new cool sounding name on an old concept, and we all get excited about it again. And I guess in the current cycle it'd be something AI or whatever. And the trouble with that is that because we're so excited about the new thing, we forget to assimilate all the hard work that has already been done and all the things that we ought to already know. I think possibly we can explain this as an example of the principal agent problem. So this is an idea from management theory that says that when one person is paying somebody else to do something, yeah, they're on.
Okay.
Can you not hear me?
No, it's fading in the back.
Fading in the back. I'll just talk louder. Principal agent problem. One person is paying another person to do something on their behalf. So the principal is the person who pays and the agent is the person who's doing the work. The principal agent problem is that it's very hard to keep those two actors aligned in terms of their motivation. So in the domain of software development, the principal is the person who's paying us to create software. And the agent is the person tapping on the keyboard, writing a code. And the principal would like the best software they can get as soon as possible for the least amount of money. But the agent's motivations are a little bit more complicated. They want to do a good job for sure, but they also want to do things that are fun, that maybe don't require too much concentration, and in particular, things that will set them up for the next round of the game. So this is the resume-driven development kind of idea. At least that's my theory for why people use Kubernetes. And other fields are not like this. So most of what everybody in this room knows about geometry is essentially what was recorded by Euclid 2,500 years ago. And so mathematics as a field has this great property that it doesn't forget. It goes through periods of rapid growth and periods of slower growth, but it's always monotonically moving in the direction of knowing more than it knew before. Every new idea builds on all of the old ones. I'd like to think that medicine works that way as well. Once we learn how to treat a particular illness, we don't then go and forget about that. But in software development, if you look back at some of the work done in the 1970s and 1980s, it can still be considered quite revolutionary in today's environment because we fail to reliably fold all that knowledge in. Now, I am certainly guilty of this, and I see it in my own work. Recently, I was working on a text-based problem, hence we have a little corpus here. And what I wanted to do, I was trying to write a program that could quickly look at a string of characters and compare it to a set of words that had previously been seen. So you can think of it like the problem that you would have if you were trying to create a spell checker. That's not what I was building, but it's that kind of idea. We get a few characters and we want to look it up. So for this example, if we started with the word thou, what I did to solve this problem was I created a novel data structure where if we have this word thou, we construct a tree of nodes. From the root, we start with T because that's the first letter in the word. The next node is the next letter in the word, so on. And then when we get to the last letter of the word, we have the actual word in the tree. So the next time I come along and I see the characters THO, I can quickly look up all of the words that have that prefix. Okay, that's the idea. If we extended it with a few other words, if you look at the, it also starts with TH, and then we'd add the E, the word the. You get the idea. I is just I, and roll becomes ROL, and then roll. So that's what I came up with, and it worked actually pretty well to solve this problem that otherwise was computationally too intensive and just took forever to run. So I thought I was pretty clever, and I was telling my colleagues about this fancy new data structure that I had invented. And unfortunately, they had to inform me that I'm not destined for computer science immortality because this thing is called a tree. And it was discovered by this Norwegian mathematician, Axel Thue, in 1912. So before they even had computers, they'd already invented my data structure. I always forget what it's called. It's called a tree because it's named after retrieval, the tree part in retrieval, because that's what the data structure does. So it's the dumbest way to name something. Anyway, my point is, it's better to know than to invent, okay? And this is why I like database technology, because unlike web frameworks, database technology really does have a wonderful history of people learning things and then those things staying learnt, and new databases build on top of the old ones, so that we can construct this kind of family tree of some well-known databases. Up near the top there, you can see IBM System R, 1974. It's one of my favorites because the people who developed System R, they wrote this really great paper about their experience and the design decisions that they had to make and why they did the things that they did. It's very readable, very interesting. And it's also remarkable how many of their ideas have persisted 50 years later. They really did get a lot of things right, many of which we'll see a little bit later on this morning. And you have this evolution where System R became IBM's DB2. Around about the same time, you had Ingress come out of the universities in California, which then led to Postgres, Sybase becoming MS SQL Server, and so on. The other thing I like about System R is the name. So originally when they were working on System R, they hadn't named it at all. So it was just like the team building the database thing. Clearly you can't go on like that. And one of the members of the team had a dog called Rufus. So they named the database Rufus and said that that stood for relational, user-friendly, universal system. But you can't call the database Rufus either, so then it became System R. For the rest of what I want to demonstrate this morning, I'm going to use an example database, which is this thing called Wormwood. It's a schemaless, read-only, SQL-ish database. And on all of the usual dimensions on which we would evaluate a database, like performance, security, reliability, etc., Wormwood is just appallingly bad, absolutely terrible. Because it was developed with just one goal, which is to be easy to understand. So it's a teaching database. It's 660 lines of code, and every attempt has been made to keep it as simple as possible so that you could open the source code while you're having your breakfast, and by the time you're finished, you'd have a pretty good idea how to build a simple database. It's implemented in TypeScript because that's kind of the most universal language that we have. And there's also a parallel implementation in Rust if you're interested in that and wanted to compare the two. So Wormwood is on GitHub. And now we'll do a little demo. As I said, written in TypeScript. Actually, the first thing I wanted to show you is the data format on disk. It takes me a while to find my mouse cursor and my other screen. Here we go. Okay. So that's what the Wormwood's underlying data storage looks like. This file, FIFA.clef, is a database of FIFA players. Each player gets a JSON object, which is one line of the text file and has a bunch of attributes about that particular player. So now with Wormwood, we can query that. By selecting from that FIFA table. And then we see the full name of all the players in FIFA. So I'm kind of ticking off the features that the Wormwood has here. We can query and we can select out particular columns. I can grab the age as well. And that then allows me to add filtering. So another feature that Wormwood has, we can say where age is equal to 41. Oh, and that crashes. What did I do? I think I forgot to put the table name in there. No. Select name, comma, age from FIFA. Age is equal to 41. There we go. It's hard to type sideways. So we can select. Certainly. Thank you. Is that better? Yep. All right, so selecting, filtering. We can also sort the results. So we have order by name descending, for example. And then one final cool party trick that Wormwood can do. It has a single aggregation, which is mean. So if you wanted to know the arithmetic mean of players in FIFA, get ready. There we go, 25.5. There were some 41-year-olds. There's even a few 42-year-olds. I don't think there's anybody older than that. It's a bit mean. Okay. Back to my slides. Okay. Wormwood is a read-only database. You can't insert data into it. So we're going to look at the read side, and we're going to do a day in the life of the query that you've already seen. Select name and age from FIFA where age is equal to 41. We'll step through the process of how a database goes about producing a result for a query like that. And the first step is to convert the query, which the computer sees as an ordered string of characters, into a data structure that the database can work with, and that's the parser's job. So a query like this goes into the parser, and we get out something that looks like that. It's a direct representation of the query they asked for, so really nothing specific to the particular database has happened at this point. We've just parsed it into something that we can work with. The next step, once we've got that, we give that parsed data structure to the query planner. And query planner is in many ways like the most interesting and most sophisticated part of the query side of a database, because its job is to look at whatever query the users come up with and then map that onto how the database actually works so that we can produce a result. The query plan that comes out of Wormwood looks a bit like that for this particular query. So it's determined that we need a two-step process to be able to satisfy this query. The first step we have is the producer step. It needs to know which table we're querying and which properties we want to look at, because the producer's job is to pull records off disk and yield them up the chain. And then the step that comes after that is the filter step, which applies our predicate that the age has to be equal to 41. And then away we go. So in Wormwood, there's this function evaluate. It's my favorite function because it encapsulates that entire process. We go from the argument input, which is a string. That's the query statement that the user entered. That goes into the parser. We get the command object out. The command object that came out of the parser then goes into the query planner. We get a query plan. It goes to the executor. And then if you look at the return type of the function there, you can see it's this thing called iter, which we'll come back to later. That's the object that the user can then use to get rows from their result set. We'll start by looking at the parser. Because Wormwood's goal is to be super simple, so the parser doesn't use anything sophisticated. There's no parser combinators going on. There's no parser generators. It's just a manually implemented parser so that you can kind of have a look and see how it works. And remember, the parser's job is to start from a string, which could be anything, and then produce an object that represents that query that our database can use. Wormwood's parser is a sequential parser, that's what the Pac-Mans here represent, is the different steps of the parser that gets applied to the string. So the first one, we have a select parser, and well, then the field parser, source parser, filter parser, whatever other parsers that we might need. So these are applied in sequence. And each parser fulfills a very simple contract, which is to say that they look at the input string. If they know how to process the start of the input string, then they chop off that bit that they understand and they produce part of the output. And then that's it. And then it goes on to the next parser. So for example, the select parser, it knows how to deal with the select keyword. So it chops that off and produces the start of the parser output. We now know that our command is a select. Next, the field parser can look at the fields we want to query out, cuts that part of the string off, adds onto the result. Source parser finds out what table we're looking at. And then finally, the filter parser can parse the predicate part and add on filter property and filter value to the output of the parser. This is what it looks like in Wormwood. Essentially exactly the same thing. So we've got a top level query parser function that produces a query object. It starts with the field parser. Each of the parsers, hopefully my laptop stays there. I forgot I need to talk into the microphones. Each of the parsers produces some result as well as that value rest. So rest is the remaining part of the input string. And then the rest value becomes the input into the next step of the parsing process. And they all follow that same pattern. They produce some output and they produce a rest. And then, of course, we put it all together in the result. Having parsed our query into a data structure, we can then give it to the query planner. And the query planner has to come up with a plan that this particular database engine can use to satisfy the user's query. And what it comes up with is this one. It's 2 steps. Produce the step to read the rows off the disk, followed by a filter step to apply the predicate and reduce it to the rows where the age is equal to 41. Now we get really to the heart of the matter, which is the way that pretty well all regular databases work when they come to answer a query is that they create a chain of iterators, or a data flow graph, if you want to think of it that way. And the iterators have an interface that looks like this. The top one here is from Wormwood. So it's an interface called iter. It has one method, next. Next can produce a row, or it can produce an end of file marker. Below that, you have an example from a sort of a textbook example in pseudocode from anatomy of a database system, but it's exactly the same thing. That is the point, is that they all work the same way. They've got a method called getNext instead of next, and it returns a tuple, which is just another way of saying a row. The only real difference is that their constructor takes an array of inputs. Because this is a data flow graph, sometimes you'll have multiple inputs, like in the case of where you're doing parallelism, or if you were to do like a join or something like that. But Wormwood likes to keep things simple, so it doesn't have joins, it doesn't have parallelism, so the iterator interface always just has one input and one output. Here I've included the source code as an example of what an implementation of the iterator interface might look like. This one is from Wormwood. It's the filter step. So the constructor has a source, which is another iterator. And that's the one that this iterator is going to pull rows from. So it's a pull-based scheme. It also has the metadata for the filter step to tell it what filter to apply. The process begins when the consumer of this iterator calls its next function. The first thing it does is pull a row from the next layer below it in the stack, whatever the source is. If it's not the end of the file, then it grabs the filter, applies the predicate. If it matches, then it returns the row. If it doesn't match, then it grabs the next row from the source, basically moves the cursor along. And then returns it. Yeah. So the executor, its job is to take the input from the planner, which is our two steps, producer and filter, and create instances of this iterator interface. So the producer step creates a producer, and the producer is conceptually quite simple. It just, when its next function is called, it just yields the next row from the underlying data source. On top of that, we need the filter iterator, which we saw on the previous slide, all of which implement this iter interface. Having constructed this stack of iterators, that then goes back to the client, and the client calls the next function on whichever is the top of the stack. And that cascades all the way down through the data flow graph, right down to pull the records off the disk and back up again, and that's how the query evaluation works. Now, this kind of chain of iterators idea is really the core idea of basically all databases and their query engines. It's there in that 1974 System R paper, and it's in everything else as well. And I really want us to make sure we have a solid understanding of that. So what I'd like to do now is do a demonstration of how this works based on this SQL query. I guess apologies to anyone who's not familiar with SQL syntax, but here we have a query where we're querying the source table. We're going to grab every record where the value n is an even number, and then we're going to produce a sum adding all of those values together. Okay, so to help me with our demo, I need 3 volunteers. It's really easy, you don't have to know anything about databases. Thank you. Number 1. Here's our database. Okay, so stand over here, I guess. You're going to be my producer. There you are. Here's the filter. Thank you very much. And sum. Thank you. Okay. Now the producer gets the database. A database is a bunch of messages. Okay. So you can hold that, pretend that's your underlying disk representation. Now I'm not part of the database, I'm the consumer of the database. What I do is, having constructed our data flow graph chain of iterators, I take the top of the stack, which is the sum, and I say, please sir, may I have a record? Okay? So you then turn to the next iterator of the stack, you ask him for a record. Can I please have a record? Have a record. Okay, now this is filter. You've got a number there in your hands, but now clearly, your predicate is n modulo 2 is equal to 0. So you're only going to yield numbers that are even. You're it's not an even number, you just throw that one away. That'll be fine. Yay! Okay, so you did ask another number.
Another one. Have the number.
You don't give up easily. Okay.
That's
Even
good.
number, you easy through Mr. Sum, okay?
I don't envy your job.
Alright. Keep going. That's the way. Beautiful. Okay. Nearly there. Okay. Now Mr. Sum gets to do all the hard work. 12. There we go.
Thank you.
From my cold dead hands. All right, thank you very much. All right. We're going to 12, aren't we? All right. Yep. Cool. All right. A little bit of complexity analysis, just to kind of bring it down again. I used to think this stuff was really boring and confusing, but it turned out to be very important to the work that I do with databases. So let's power on. The idea here is that we want to have a scheme to quickly categorize algorithms based on how the amount of work you need to do changes with the size of the problem. We talk a lot about this thing called n. So that is the variable that we take to represent the size of the particular problem that we have to work on. So then we get this notation, big O of n or order of n. What does this mean? Well, what it means is that the amount of work we have to do, the y-axis, increases in proportion with the size of the problem. Most things in life you could think of as working this way. If you need to like dig a hole or build a wall or whatever, twice as big a hole is going to take twice as long. That's what that means. So from the point of view of someone building a database, a slightly worse complexity would be this one, order of n squared. This is called polynomial time. We know it's polynomial time because the n is in the base position and the exponent is a constant. It can be any constant. It could be n cubed or n to the fourth. Doesn't matter. They're all polynomial time. So polynomial time, it's worse because if we double the size of the problem, we more than double how long it's going to take. Examples of this are things like pairing all the values in a list, or from a programming perspective, anytime you have nested for loops where you're iterating over a collection twice, those algorithms are polynomial time. Things get really bad with exponential time. And here you can see that the constant and the n have swapped positions. We have a constant base and we have n is in the exponent position. So these algorithms are problematic. An example of this one would be so calculating permutations and combinations. If we had a 32 character password that we wanted to try to brute force, and it's Unicode, so each character can be one of 149,813 different characters, then we get that number to the 32nd power possible combinations, which is the number at the bottom of the screen there. That is 165 zeros. It's really, really terrible. So then for some good news, we have some algorithms go the other way. So you can have an algorithm that is order of log n, and in these ones, as the size of the problem increases, the amount of work increases, but slower. So that could be things like, I guess like a real world analogy would be maybe something where every time you do the task, you get a little bit better at it, so subsequent ones are faster. In computing, a common example is, and a relevant one for today's topic, is looking up data with an index. Is typically order of log n. So what about things like order of 2n? Because this kind of analysis is asymptotic analysis, we're concerned with what happens as n approaches infinity. And in that particular case, n and 2n turn out to be the same. So we just chop off the constant multiple and can ignore it. This brings me to indexes. So probably we've all had, or hopefully, some kind of experience with indexing. In your typical database, it very quickly becomes impractical to do any kind of query at all without having an index there that can serve that query. The reason for that is, say if you're thinking about a relational database and you want to find a particular row, that operation without an index is order of n. So every time the size of the table doubles, so does the amount of time it takes to find your row. That's the reason why we create indexes, because they help us answer queries faster. There's also reasons why we don't create indexes. One problem with indexes is that their property is to make queries faster and inserts slower. Also, they can create a lot of extra data on disk that you have to worry about. So there's usually a trade-off there to decide when an index is going to be worthwhile or not worthwhile. The picture here is from the index of a book, Programming Rust 2nd edition. And it's there because it's a very rare metaphor where the index in a book is not just like the index in a database, it's exactly the same. If you've ever used the index in a book, that's precisely how the indexes you use in databases work. If we, each entry you can see has a key and a value. The key is the thing that you're looking up, some kind of term that appears in that book. The value is the page numbers where we can find that information. Those index entries are sorted alphabetically and they're grouped by the first letter. So with Programming Rust 2nd edition, if we wanted to find the term generic enums in this book without an index and without sorted data, the only way you could do that would be to start at one end or the other and just work your way through the entire thing looking for that particular term. That's a full scan, that's order of n. If you had a very weird copy of Finding Rust 2nd edition where all the terms in the book were sorted, then you could do better and we could do a binary search. Binary search picks a middle value in a sorted data set, and either our term is smaller or larger than that. So either way, we can immediately cut the search space in half. And then the algorithm just repeats that over and over again until it finds the value. So binary search is hugely important in databases, and it's order of log n. Now in the index case, and Programming Rust 2nd edition does in fact have an index, then we can do much better. We want to find generic enums. We go to G in the index, then we search for generic enums within the sorted index entries. Because they're sorted, we could in fact perform a binary search within the letter G if we wanted to, and that's how that works in the book. The picture here is of a B tree, which is the database equivalent. So the keys of our data set are organized into a tree structure. And in between the values in the tree, we have pointers to child nodes. And where the pointer is indicates if the values in the child node are smaller or larger than that particular key. So from 7 here in the root node, everything in the pointer to the left has to be smaller than 7. And everything in the pointer between 7 and 16, that child node has to be between 7 and 16. If we were to use the B tree to find the key 8, we would start at the root node. We would compare 8 to 7. We would notice that 8 is larger than 7, so we'd move along. We'd compare 8 to 16. We would notice that 8 is less than 16. Therefore, we'd follow the pointer to the child node. Compare 8 to 9. We'd notice that 8 is less than 9. and there is no child node there, and therefore we would know that 8 is not in our index. And often that's what you want from your index. You don't actually necessarily need to find the value, you just need to prove that it's not there. It occurred to me at this point in creating these slides that the index in a book is in fact a B tree. It's a two-level B tree with a branching factor of 26. So comparing binary search and the B tree, binary search requires sorted data and is big O of log n. B tree requires index data and is also order of log n. Do these complexities mean that they perform the same? No. So from the perspective of complexity analysis, they have the same complexity, but they actually have a different base to the logarithm. So we can basically say that B tree works better. It's just that it requires an index, not just sorted data. Okay, Wormwood has indexes, and this is what they look like on disk. If we create an index on the FIFA table and the age property, we will get an array for every age in the data set. And the items in that array are the line numbers of FIFA players who are that particular age. So when we run the query in the presence of this index, rather than brute forcing through the entire data set, we can immediately jump to the age that we care about, grab those line numbers, and get the data directly without having to do quite so much work. So let's have a go at that now. Firstly, we'll just run the query. Okay, and I want to take note of the evaluation time there, 187 milliseconds. Now I can create my index on the FIFA table and the age property. So that's gone and written that data structure to disk. Then the next time I run the query, it'll automatically detect that index. And actually, the problem of detecting indexes is also a really interesting database topic. And now the query evaluation is 112 milliseconds. It got a little bit faster. It didn't get that much faster, and the reason why is the problem is this really this disk format that Wormwood uses. If I, for example, know that there's a player who's 17 and they're on line 4,783 of the source file, the problem is that to find that row in the source file, because it's new line delimited JSON, the only way to do it is to iterate through the 4,782 lines that came before. So it doesn't save as much time as it would if you had a database like, say, Postgres or something like that. The rows in the table have a fixed size. So you know if you want to find the 4,783rd row, you can just immediately jump straight to it. It performs much better. Cool. Okay, so databases are amazing. Hopefully you can agree with that. If you're interested in having a look at the 660 lines of code that make up Wormwood, it's on GitHub. You can find that. The read side of a database is implemented as a chain of iterators. Just remember that our chain of iterators who kindly volunteered to demonstrate how that works. Indexes are not just like book indexes, a book index is a database index. The subscript of logs in big O notation doesn't matter, except that it kind of does. If one way of doing it is twice as fast as the other way of doing it, as a database developer, I do care about that. And questions. I've got prizes too for like people who ask cool questions. These bamboo socks. They're very nice, very popular. Yes. So I mentioned before about how you find which index to use when you're trying to execute a query. And that was something that I had to work on for Seek. And as part of my research into the best way of doing that, I cracked open the source code for Postgres, and it is remarkably approachable. It's written in C, and I haven't touched C for 25 years, but it's just commented so well. I didn't even read the code so much as I just read the comments, and I was able to find the bit of code that does the index choosing, and I was able to work out how it works. So I think Postgres is a really good place to start.
What's your favorite database?
Well, there's a little database called Flare, which is written in Rust. That's the one that I work on. It's pretty cool. But I'm a huge Postgres fan. I just love everything about Postgres, except that, maybe it could be a bit easier to use, but it's an awesome database.
Are there a big difference between disk-based and memory-based databases and how they operate in?
I don't know much about memory-based databases, other than that I guess all databases have kind of like an in-memory part to them. I've been thinking about this recently. I don't get in-memory databases really. Like Redis is cool, but the problem I would think is that, so you can get up to a terabyte of memory, so fine, we can have a terabyte in-memory database. But if you're spending $300,000 or $400,000 a year on a database server, the first thing that's going to happen is you're going to want more than a terabyte. And there are so many things that we can do and do to make disk-backed databases perform really well that I guess I just don't know much about it, probably. I don't see the value, which probably means that I just don't know what I'm talking about. Yes?
I noticed there was evaluation time for your queries.
Yeah.
But when you created the index, it didn't have an evaluation time.
Yep.
Anyone notice any changes based on the data set on how long the creating index is?
Yeah, that's a good question. Yeah. First thing I wonder is like, well, is it order n? I don't know. So I think the file here is about 25 meg of text, of JSON. And Wormwood is slow. It's really slow. 100 milliseconds is terrible. It's written in JavaScript, so like, what do you expect? The index creation process, it would be similar, because it really does the same thing. It just has to run through the entire data set and apply the predicates, and it just kind of, basically it's the same operation, it just saves all the results. Yeah, and of course there's like the I/O that's involved. Yeah.
What's your opinion on count? Well, you gave them some. Does count have some separate magic to it, or does it also take through a chain of iterators and record one by one?
Yeah. So this is where. Oh, sorry. So the example that we worked through was a sum aggregation. So the question is about count and if there's any special properties of count. So this is where the query optimization gets really interesting, because what you can do when you have a count query is you can notice that it doesn't matter so much what you're counting. You're just counting that there was a thing. So when you do the when you do the query planning, a common way to do it is firstly to build a sort of naive query plan, which is just like a thing that will work. And then you have multiple optimization steps that transform the query plan in such a way that the result doesn't change, but the execution is faster. And the kind of thing you can do is like drop out a whole heap of work for counts. You could have an iterator that just yields trues, for example, and we just count those because we don't care. The one that is really interesting is mean, and particularly in the parallel case, because if you think about, if you wanted to do a parallel algorithm for mean, it changes. There's quite a bit of work you have to do. It's not as simple as count and sum. You can split count and sum trivially and then combine the results, but for mean it's a little bit more complicated. And percentile you can't do at all. Yep.
What does the data format of this look like for like a real database? It would be based on
So the question was, what does the data format on disk look like for a real database? Hugely varied and very, very, very important. Databases essentially operate on disk. You can't really, well, very often you can't bring things into memory. The whole operation, say like the application of indexes is all done on disk. We don't load a B tree into memory and then do things. We do it directly on the disk. if you know the data types, then there's a lot of packing in of fixed number values. You know, we'd have, this is why your database requires you to say what size of numbers you want to store in a particular column, how many characters of text you want, because they're trying to pack that data in as tight as possible. Compression is a really big deal as well, and an active area of research, particularly in column-oriented databases, because when you store the columns all together, there's lots of additional things you can do to get really great compression. And we don't care about compression because it saves disk space. We care about compression because it saves I/O bandwidth.